Hello, welcome to a quick video lecture on for AP students on how to use and interpret PV or pressure volume diagrams. I'm going to try to make this fast and spend most of the time practicing these things on when we're together in class. So a little bit of background knowledge. What do you need to know going into this? Definitions of isovolumetric, isothermal, and adiabatic. I'm also going to add to it another one, which will be pretty simple, one called isobaric. Baric meaning pressure, like a barometer measures pressure. First law of thermodynamics for the above processes. So those, as simple as the first law is, it simplifies even more for those processes. And then the other thing, we have to go take a trip in the Wayback Machine for those of you that took chemistry. So we have to discuss the combined gas law or the ideal gas law, and I'll just show you the important part of it. If we look at the ideal gas law, PVNRT, PV equals nRT. For a sealed system, a system that is not allowed to add molecules or atoms or remove them, and the number of moles will be constant, R is the universal gas constant. So what we get then is P over PV times T equals some constant value. And that's why we can say the idea or the combined gas law is these at one state, if we make a change, that ratio of P times V over T has to be the same. So again, here's the ideal gas law. Here is the combined gas law. They're really telling us the same thing in this regard. A PV diagram is a pretty simple thing to think about. Initially, it's just a regular kind of Cartesian X, there's a Y. P is traditionally put on the Y-axis and V is traditionally put on the X-axis. But you'll notice we've got these strange kind of curving lines here in this case, and I'll tell you what they are called first and show you what they mean. These lines are called isotherms. And their significance is anytime we plot a pressure and a volume and that point lies on these isotherms, they would also have the same temperature. And the reason is, why does it have this shape, is if we think about having a constant temperature, that means T is constant. N, remember, is constant, and R is constant. So really what I could say is PV equals some constant in this instance. Then P is equal to a constant over V. So we see that there's this inverse relationship between pressure and volume, so we see that hyperbolic shape to that curve. The mathematics, for reasons why it's curved, is not super important. What you do need to understand, though, is any point on this isotherm, even though they may have different pressures and volumes, will have the same temperature. So if we use our combined gas law knowledge here, we'll notice for this point right here, pretty low volume but a pretty high pressure. We get big pressure, little volume over some temperature. And that ratio should be the same here too. This one's a little bit different, right? It's got a low pressure, but the product of the numerator is compensated by having a larger volume, and the temperature is the same anywhere on that isotherm. So another important thing to understand about isotherms is how do you read it? How do you know which isotherm is hotter than another isotherm? Well, again, we can use our combined gas law knowledge to do that. This point represents, we'll compare these 2 points. This point represents a lower pressure and a lower volume than this point. This point exists at a higher pressure and a higher volume. If the combined gas law says that these ratios need to be the same, small pressure times a small volume will need to be divided by a small temperature. A big pressure times a big volume will need to be divided by a larger temperature in order for these two ratios to be the same. To make a long story short, what that means is as we read this direction, as the isotherms go from here to here to here to here, this is the hotter isotherm and this side is the colder. So once we've learned what an isotherm is, identifying an isothermal process, and remember that means that the change in thermal energy is zero. Our first law simplifies to that. An isothermal process is pretty easy to identify. It's going to be a process, if we start at state 1, that will stay and go to state 2, it will always follow track right on that isotherm, and I kind of came off there. It should be right on that isotherm in that case. So we could refer to this if we were moving in this direction, right? Our volume is increasing. We call that isothermal expansion. But we could also have the state 1 or the first state down here. Let's just do it on another one. And end up here. Again, I came off that line. And moving in that direction, that would be isothermal compression. So that expansion or compression is a result of heat added or removed from the system. Now, adiabatic process we could also identify on a PV diagram. Remember, the definition of that is no heat is transferred in or out of the system. So Q is 0, and our first law simplifies to this. A change in thermal energy is achieved by doing work on the system or having the system do work on the environment. It's going to look similar to the isothermal process, but the differences will be subtle but important. So let's first consider the case of adiabatic compression. So we would start at state 1 here at a pretty high volume and a pretty low pressure in this case. And we know what's going to happen if we... Whoops, screwed up there. All of this stuff is right. The stuff I had drawn on the PV diagram was going to lead to incorrect statements. So I think I have it fixed here. Adiabatic compression, if we start at state 1 at this volume and we want to go to state 2 at this volume, we're compressing it. The volume is decreasing. So the path would look like this. But we also know from experience when we compress a gas, it heats up. So an adiabatic process is also going to be a curved line because we still have that inverse relationship between pressure and volume. But the curve will actually go across isotherms. So when we compress it, we expect it to warm up. We should go from a colder isotherm, which is this one, to a warmer isotherm. So adiabatic expansion should show us the opposite. So here we're going to go from state 1 at this volume to state 2 at this volume. So the volume's increasing. We know when air or gas is allowed to adiabatically expand, it should cool down. So we're going to see a adiabatic path go in this direction. So that would represent cooling. Now we'll get better at this with practice, but look how subtle some of these are right. The two that I've just shown you are correct, but look how similar it looks to this one. What if I were to draw and think that this was a correct adiabat or an adiabatic process? We start at state 1, we compress it, so we're decreasing its volume, and we end at state 2. It kind of looks like this curvy line. They all look the same, right? But we've got to think about what happened. In this case, we compressed it, so it should warm up. But our line went from a hot isotherm to a colder isotherm. So we do have to be careful to catch those small differences. We'd always expect for compression to go from an isotherm to a hotter isotherm. So that might be a correct route. Okay, for an isovolumetric process, isovolumetric means no change in volume, which means that the work term, because it's calculated with the change in volume, has to be equal to 0. First law of thermodynamics then becomes the only way to change a system's thermal energy is through adding or removing heat. Man, isovolumetric is going to be so easy to identify. It means volume doesn't change. So an isovolumetric process would just be a vertical line on your PV diagram, right? If it doesn't allow it to move anywhere in this direction, there's no change in volume. So that'll be an isovolumetric process. So a new process for us, but pretty simple to understand, is something called isobaric. Isobaric means that there's no pressure change. So the P needs to be constant, and we've really been treating problems mostly that way anyways. We won't actually simplify the first law of thermodynamics, but it is useful for a PV diagram. Isobaric process would be something open to the atmosphere, where the pressure isn't changing. Simple to recognize also on a diagram, because if P doesn't change, we're going to see isobaric processes as horizontal lines in that case. Why this is important, because it introduces us a little bit. If I take a look at work, remember, is pressure times a change in volume. Well, look what I have. I have some pressure here and I have some change in volume here. So there's a little bit of calculus. If we have a line like this, it's real simple to calculate the work that was done on or by a system just by calculating the area underneath the line of on the PV diagram. If the isobaric process goes in this direction, from state 1 to state 2, that's expansion. So we would say that the work done by the gas is positive. The work done on the gas would be negative. If the isobaric process goes in the other direction, from state 1 to 2, this is compression. We would say that the work done by the gas is negative, and the work done on the gas is positive. Okay, that is it. You're certainly not going to be an expert from this 10-minute video, but we will practice these things together and see what the significance of these PV diagrams are by putting them in cycles together in class.